All right. Well, I'm going to talk about how to. Well, thanks, Peter. I'm going to talk about how to use modeling effectively to determine the critical parameters for designing a passive venting system. The same thing can be used for active venting, but today my focus is passive venting. Um, So passive venting systems can be represented by these two schematics mainly. One without ventilator turbine assistance and the one with ventilator turbines. The one on the left works with stack effect, which Andrew has actually dived in quite a bit into. Critical design parameters for a sub-slab ventilation system um, consists of radius of venting influence. That is how far apart we need to be placing the vent laterals. And for effective venting of the entire space that is between the two vent laterals. And then projected airflow in the vent riser, how much air we expect, the vented air we expect to go through the vent riser, and then vent riser sizing, how big the vent riser need to be, and ventilator turbine sizing. In the case of when we are using a ventilator assisted passive venting system, we want to know what size of that ventilator turbine we need to be installing. Again, today for the passive venting system, I'm just talking about the venting system design, not the vapor barrier design per se, which is an integral part of a passive venting system. So here are the factors that affect the ventilateral spacing. The lateral spacing is directly proportional to pneumatic conductivity of the aggregate layer. That means the higher the permeability of the aggregate layer, the higher or the farther away the vent laterals can be spaced. And it is inversely proportional to native soil conductivity. This is something most often we don't pay as much attention to, which needs to be paid attention to, is that the tighter the native soil, the farther away can be the spacing, and then uh, the more conductive the native soil is, the closer needs to be spacing. And then lateral spacing is directly proportional to the induced vacuum. So through the vent riser, whether we're using we're using stack effect or we are using a ventilator turbine, we are essentially inducing a vacuum to the subslab environment. And that the higher the vacuum we are inducing, or we are able to induce, the farther away we can space out these laterals. Traditional approach has been for the design of passive venting system has been pretty much we have been spacing them 50 feet apart. And where is that coming from? It's coming from basically the guidance that I could find, at least provided by EPRO and ITRC. EPRO says 50 feet spacing. ITRC says maximum 50 feet you can space them out. But I could not find any published engineering basis available for these guidance. So the problem statement for this is that venting effectiveness with vent lateral spacing of 50 feet is uncertain, because we do not know, if we space out at 50 feet, whether the entire space between the two vent laterals are going to be actually vented out or not. Smoke testing, sometimes we do smoke testing to, post installation smoke testing to see the venting, but it's really no indicator of venting effectiveness. But all it says is that the the vented out space is continuous. That is continuity of the space between the two laterals. And the laterals themselves. So, and the need for a tool based on engineering principles. So, therefore, there is a need to develop a tool based on engineering principles that we can rely on in designing these venting spacing of vent laterals. So, this is the schematic showing basically the airflow through subslab. One of the things to understand is that all air comes from the atmosphere, and then the arrow in the middle that you see pointing up is basically the location of the vent riser, and there is this aggregate layer providing the permeable acting as the permeable layer for that venting. And so all air comes from atmosphere and then basically goes around the foundation, ultimately enters the permeable layer and gets vented out. And most of the airflow that we are talking about in venting is really shallow airflow, not deep. We are not getting air from deep underground to be vented out. It's all coming from the atmosphere, going around the foundation and entering traveling through the vent laterals and entering the vent riser. So the schematic that I presented can be mathematically described by a differential equation for basically know that the idea is not to present the differential equation or how the differential equation can be arrived at, but the idea is know that it can be mathematically described. The vacuum at every point away from the vent riser can be described mathematically for that schematic. So for that differential equation, there exists a solution. Actually, Digley in the field of groundwater has come up with a solution to that form of equation, and that's what I have adapted here. Is that for distance, as you go further away from the vent riser, at some point the induced vacuum will go to zero. And then knowing that boundary condition at the far away and at the vent riser, you can come up with a solution. And this is what Digley solution. This is the famous Digley solution that vacuum can be expressed as a function of distance. That means at any distance you can describe this vacuum, knowing the flow or the extraction rate at the vent riser. So using this equation, you can fit this into a spreadsheet and come up with basically degenerate system curves. That's a relationship between vacuum at any distance and then the airflow and the radius of influence. That means you can set a threshold for your threshold vacuum for your radius of influence, and you can come up with radius of influence. For passive venting system, I set the threshold to be 0.001. For active venting system, it's state dependent. In Michigan, we set it at 0.02 inches of water column. So for the following assumptions are used in this model is that airflow in the aggregate layer is laminar and Darcian. Aggregate layer is homogeneous and isotropic, and a certain quantity cannot exceed the value of 3. Now we can come up with the vacuum induced by a ventilator turbine using a simple equation, and then apply that to apply both. So what you're looking at is a situation where we have an existing slab and we have this vent, these 3 points where we have vent risers to vent out the subslab, existing subslab, and then we have a new construction, if you will, that is basically a cutoff trench filled with Asto 57 stone, which is a very coarse stone, and then we are venting out that space as well. So that kind of serves as a new construction type of scenario. So compare, and then using that simple equation, came up with that the predicted vacuum induced by the ventilator turbine is 0.04 inches of water column, and then you can come up with system curves, and then for using the Digley solution, and then for 0.04 inches of vacuum, we selected ROI of 3.6 for existing slab, and then airflow rate of 1.8 CFM. And then for the new construction, which is the back trench, cutoff trench, we got an ROI of 20 feet and an airflow rate of 36 CFM predicted by the model. And then when we compared model predicted to the actual measured after installation, we find that vacuum, this is for the subslab, existing slab. So model had predicted 0.04 inches of vacuum, and then we measured it as any measurement varied anywhere from 0.003 to 0.016 inches of water column vacuum. And then air extraction rate, model had predicted 5.4, measure was anywhere between 1.5 to 12 CFM depending on wind speed. Model prediction was for 4 miles per wind speed, which is pretty good in the middle of the value. And then ROI, model predicted 3.6. We came up with the actual measure is somewhere near 3.4. And then for the cutoff trench, the model predicted 0.04 inches of vacuum, and then maximum recorded was 0.01 inches of water column vacuum. Air extraction rate of 36, maximum recorded of 29, and then ROI of 20 feet, and then we got more than 15 feet of ROI. So which is pretty good agreement with the model predictions. Takeaways are effective ventilateral spacing are not one size fits all. So you need to you can't just use 50 feet of spacing in every situation. Digley solution can be modeled into a spreadsheet to develop system curves, and then modeling is successfully used to provide an engineering basis for ventilateral spacing and ventilator sizing in this case. Thank you.